Hey everyone. So in today's class, we are going to do the problem solving on linear regression and logistic regression. So let's see how our DF looks like. So we did pre-processings, removed unnecessary columns, and converted or encoded our objects or strings into numbers. And this is how now our data looks like. So if you see, there are 205 rows. We have also done the outlier analysis. That's why the number of records have become less. We have removed serial number and then we have converted the strings into numbers as well. That is, did the label encoding. So now this is our data set and we have gender, SSCP, SSCB, HSCP, and so on till salary. Now let's first perform linear regression. So let's have linear regression. Okay, so let's first check the head and can you figure out what should be the target? So basically, let's figure out our salaries on the basis of gender, SSCP, SSCB, and so on. Okay, so basically, we are trying to predict the salary on the basis of gender, SSCP, SSCB, HSCP, HSCB, and so on till status. Okay, so let's first try to see the correlation between the salary and the all the other attributes. Okay, so if we see, let's see the last column. So this is basically the correlation that salary has with gender. Then this is the correlation which salary has with the HSCP. If you see, HSCP is the second one. Then, sorry, SSCP, not HSCP, SSCP. This is the one with SSCB and so on. So if you see, your salary is linearly correlated, but not very strongly correlated. The strongest that we get is zero point 0.9. So salary is strongly correlated with status. Obviously, if we know that the status is zero, that means the salary will be zero. And if the status is non-zero, then the salary will be non-zero. So what I'm trying to show here is that probably linear regression is not the best model for this data set if you're trying to predict the salary. The reason is that the correlations that salary has with all the other independent attributes are not very high. Okay. But let's see how the linear regression sails in this data set. Okay. Now, first thing is that we will extract our target and all the independent attributes. So let's say we have x1, x2, x3. All of these are independent attributes. And then we have a target attribute. Okay. So all of these independent attributes will be treated as x and this will be written as y. So that's what we're going to do. Okay, so let's do it here. So first thing, let's take all the columns except salary. So basically I'll use ilog. Ilog is basically used to take the records and the columns based on their indices. Okay, I want all the records. So basically that's why I'm going to put a colon. And then the columns, I want all the columns except the last one. So to exclude the last, I can write -1. Okay, so let's see how does it look like. All the records will be taken. And if you see, your salary is gone. Now, let's put this in X. Okay, let's put it in X. So now our X will basically be the data frame which has all the records and all the columns except salary. Then if we need our Y should be what? Basically our target attribute only. So all the records for that column and only that last column, which is basically given by -1. So it will basically be our salary. Okay. Now, what we will do is instead of providing the data frames, we'll provide the values. Values, that is, we'll provide the arrays. So basically, we are instead of providing the data frames, because generally the models they accept arrays. So that's why we are going to convert them into values. And what will values give us? Values is going to convert the data frame into arrays. So if you see your x is basically a data frame which has rows and columns. So it will be converted into which kind of array? It will be converted into a 2D array. Let's see x. You can use np.array also, but there's another function, there's another attribute called values. If you just write it like this, your data frame will be converted into a 2D array. Why a 2D array? Because there are multiple records as well as multiple columns. Okay. Now, similarly with y will be converted into 1D array. The reason is that there is only one column here. So we use the attribute values. And now we have our y. So basically now we have x, which has all the independent attributes, and y, which is the target. Now, what we will do, the first step that we have in supervised learning is that we have figured out our x and y. That's the first step. The second step is that we split the data into training and testing. Okay, so we are going to divide the data. The first bigger chunk is going to be training. And obviously, it's not that the first 70% or 80% of the records are training. No, that's not the case. The data, 70% of the data will be selected randomly and given to the training set, and then remaining will be given to the testing set. Okay, now it depends on you, whatever percentage you want, but your training data percentage should be higher. Okay. So, how do we do the train test split? So, for that, we are going to use sklearn. Now, what is sklearn? We've already discussed. sklearn is basically a very powerful Python library which can be used for lot of pre-processing, lot of model buildings. We don't have to provide, we don't have to write the complete code. We just need to provide our data. We just need to set a few hyperparameters. We just need to tell what model we need to build, and sklearn is going to do that for us. So sklearn is the most useful and robust library for machine learning in Python. It provides a selection of efficient tools for machine learning and statistical modeling, including classification, regression, clustering, dimensionality reduction, and so on. Classification and regression we'll see. We'll also see clustering. We'll also see dimensionality reduction, that is principal component analysis. And this library is built on top of NumPy and Matplotlib. Okay, so the first step obviously was to get the x and the y. The second step would be to split the data set into training and testing. Okay, so we are going to use sklearn for that. So from sklearn dot, now here we have to import the train test split, and the train test split is actually inside model selection. So if we do control space, we get model selection, and from here we have to import train test split. So when you see these things for the first time, you might not remember, train test split comes from model selection. But when we keep on doing this for multiple times, when we build multiple models, you will have this in your head that train test split always comes from model selection, linear regression comes from linear model, and so on. So don't worry, things are new, but as we go, as we build multiple models, these will become familiar and you will be acquainted with them. So import train test split. Now we are going to use this train test split to split our data into training and testing set. So we write train test split, and then here we have to provide our x and y. So the first one is basically your independent attributes, and the next one is your target attribute. And there are multiple other things also that you can provide. So one of the things, one of the parameters in the parameter list is basically the test size. Basically, how much data you need uh, to be a part of testing and how much should be a part of training. So if I set, let's say, zero point 0.3, that means 30% of the data goes to the testing set and 70% of the data goes to the training set. Okay. And by default, the value of this test size would be what? 0.25. Okay, by default it's 0.25, but we are setting it to zero point 0.3 here. So let's see. What does it give us? Let's check. So it gives us multiple arrays. The first is a 2D array. The second is also a 2D array. Let's see. The next is a 1D array. And if you see the numbers, these are big numbers, which probably are the salaries, right? So even if we don't know what these arrays are, we get to know that these are big numbers and there are zeros. So it's the salary column. And then the fourth one is also basically a 1D array. So the first two are 2D arrays and the next two are 1D arrays. So the first two are basically our X, which was basically our 2D array, and the next is Y, which was our 1D array. So the first one basically is your X train. So if I have to write, this would be X train. So the first 2D array that we get is our X train. The next 2D array that we get is our X test. The third 1D array that we get is basically the Y train. And the fourth one that we have is Y test. So these are the four that we have. Okay. So basically first one is X train, second is X test, third is Y train, and fourth is Y test. Okay. So now if you see, I can just write them down. I can just say A comma B comma C comma D is equals to this. So the first array would basically become A. That is, A variable will store the first 2D array, B will store the second 2D array, C will store the third array, which is 1D, and D will store the fourth array, which is again 1D. So instead of writing it as A, B, C, D, I can give probably more meaningful names. So the first one we know is X train, the second one is X test, the third is Y train, and the fourth is Y test. Okay, so this is how we can get our X train, X test, Y train, and Y test. So let's see our X train. It's a 2D array, right? X test will be 2D, Y train will be 1D, and Y test again will be 1D. Now there's another parameter that you can set here, which is called random state. So what does this random state parameter do? So random state parameter is used for initializing the internal random number generator. So basically what happens is randomly some of the records go into training and some records go into testing, depending on the percentage of test size that you set. Now basically to randomly pick the records to go into training and testing, there is a random number generator, and basically random state is used to initialize that internal random number generator. To understand what is the specific use of this random state I can show it to you here. So you can set it to any value. Let me set it to 42. So what will this random state actually do? It is going to help us get the same training and testing data whenever we run the train test split. Let me show it to you before this. So let's see. If I just write train test split and just give my X and Y and say the test size is 0.3, if you see, if you just see from the top only, you're getting 0, 60.3, 0, and so on. Let me do it again. And you see the values change. Let me do it again. The values further change. So basically, if you just write this, whenever you run the model again, your training and testing data is going to change, and in turn, your model performance or RMSC, MSC, R square, all are going to change. So because if the data changes, then obviously there would be some change in the evaluation metrics also. So whenever you run this, every time you're going to get different results. To prevent that, to get the results consistently, I should set a random state. If I set random state is equals to, let's say, 42, or you can give any value, 42, 43, anything, or you can give 1, 2, any value that you give, it's up to you. You will always get the same training and testing data. So if you see, we can check it from here. You have 0, 88, 0. Let's run it again. You'll still get the same results. So anytime, if you've set random state to be any value, anytime you run the model, you always get the same results. So 0, 88, 0. Let's check again. 0880, 171.43. Let's again run it. You see, you're always getting the same results. You're always and always getting the same results. So this is the advantage that random state is going to give us, because anytime you run the model, you'll always get the same training and testing data. And once you build the model with those, you'll always get the same evaluation metrics. Okay. So that's why random state is an important parameter. So now I'll write it here like this. Okay. So now we have our X train, X test, Y train, and Y test. No matter how many times we run it, we are going to get the same X train, X test, Y train, and Y test. Okay. Now the next step that we have is, if you see your X train, you will see that different columns have values in different scale. So basically, if you see the first column, or you can see your DF also, the first column had gender, which was in the range 1 to 0, then SSCP, which was in the range 0 to 100. Now, why is this a problem? Is this a problem, or it's fine? It's actually a problem because what happens is that different features are in different scales. Some are in the range 0 to 1, some are in the range 0 to 100, some could be in the range 0 to 1000, some could be in another range, some could be in any other range. So if different features are in different range, then that can be a problem. Why? Because your models can interpret that the value, those columns which have higher value, they are of more importance. So that can be interpreted by your model. That's why we should do feature scaling. That is bringing the features in the same scale or almost the same scale, so that all the features are treated equally by the model. That's what is basically the concept of feature scaling. So feature scaling is a method used to normalize the range of independent variables or features of our data. And it's only used to normalize the range of independent variables. You don't need to normalize or scale the target, which is salary in our case. Why don't we need that? Because we are concerned by these. So when the model is will be built, these features are going to be compared, and basically it will be figured out which are related to Y in what way, right? And also, if you do this feature scaling of Y, then the problem would be these values are going to change. The X values are going to change. If you change your Y values also, then for a new point that comes in, you change its X values for feature scaling, and the Y that you get is not going to be a big salary. It's going to be some small value, or it's going to be on in that range in which you have done your feature scaling. So you'll not be able to interpret that answer that you get. I'll explain that in a while. Don't worry. So we are here, right? Now what we want to do is we want to do the feature scaling. Why? I've already explained that to you. There are two ways to do feature scaling actually, and I will explain you the ways. Give me a second. So there are two ways, generally two ways. There are multiple ways, but the common ones are normalization and standardization. Okay. So let me take an example and explain this. So let's say we have multiple columns. We are interested in one column. We actually understand it on one column and then we do the same for all the other columns as well. So let's say this is how the column looks like. These are the values. Okay. So in normalization, which is also called as the min-max scalar, we figure out what is the x min, what is the minimum value that we have here. It is 0, and the x max is going to be 10. This one. So min is 0, max is 10. Now, what do? We transform all the values by this x minus x min, x1 minus x min divided by x max minus x min. Okay, so basically, what will 6 be transformed to? 6 is the value, right? So now what is x min? It's 0. What is x max? It's 10. What is x min? It's 0. So it will basically become 6 by 10 or 0.6. Similarly, this would become 0.1. This would become zero point 0.4. This would become zero point 0.3. This will become 0 and this will become 1. So basically what does this normalization do? It scales the feature. It scales the column into 0, 1 range. So whatever, be it this or be it anything, it's going to scale up or scale down the features into 0, 1 range. So after the transformation, our column is going to have all the values in the range 0 to 1. So this is the transformation that we do. Now all the features would be in the 0 to 1 range. So now all the attributes are equal for the model. So that's what normalization is. So normalization is a scaling technique in which values are shifted and rescaled so that they end up ranging between 0 to 1. And it is also known as min-max scaling. Okay. Moving on to the next scale. So this was normalization. The second scaling is called standardization. So here, let's say we have 6, 8, 5, 4, 0, 3, and so on. So here, what do? The transformation that we apply is basically x minus mu by sigma. And it is generally used when we know that the columns have normal distribution, normal or the Gaussian distribution. What is normal distribution? It is basically a bell-shaped symmetric distribution about this point. So whatever is on the left is exactly the same on the right as well. So here what do is we transform it in this way, x minus mu by sigma. What is mu? Mu is the mean of the column. So basically mu is the mean, 6 plus 8 plus 5 plus 4 plus 0 plus 3 divided by the number of points, right? That's what your mu is. And then we have sigma. That is the standard deviation. So basically we find the mu and the sigma and then we do the transformation as x minus mu by sigma. So let's say the mu is some value. Let me just write it as mu only and sigma as sigma. So this would become 6 minus mu by sigma. This would become 8 minus mu by sigma. This would become 5 minus mu by sigma. This is 4 minus mu by sigma, 0 minus mu by sigma, 3 minus mu by sigma. So this is the transformation that we do. And remember, either you do normalization or you do standardization. It has to be done for all the independent attributes. Okay. Now, in standardization, what's the benefit? The benefit is that the column that you get after the transformation, it will have mu is equals to 0 and sigma is equals to 1. They won't be in the fixed specific range like 0, 1. No. But here, the mean of the transformed column would be 0 and the sigma is going to be unit 1. Okay. So So standardization is another scaling technique where the values are centered about the mean with a unit standard deviation. This means that the mean of the attribute becomes zero, that is mu is zero, and we have sigma as one. And this is the transformation that we do. Now you will ask me, which is better, normalization or standardization? There is no exact answer to this. So what you could do is you could build one model with normalization, another model with standardization. So basically build one model in which you've used normalization first and then build the model, or let's say in our case it's linear regression. So first you do normalization and then perform linear regression. In the second case you do standardization and then perform linear regression and see which is giving you better evaluation metrics or better results. But I can give you some suggestions. So whenever there are outliers, because since here we are doing x minus x min by x max minus x min, x min and x max will be affected by the outliers. So if there are outliers, then you should prefer standardization because normalization will be affected by outliers. And standardization is generally used when we have the columns having normal distribution. So let's read through this. Normalization is good to use when you know that the distribution of your data does not follow a Gaussian distribution. So Gaussian is basically normal distribution. And standardization, on the other hand, can be helpful when you know that your data follows normal distribution. However, this is just a suggestion. It's not necessarily true. Standardization would work when we have outliers because normalization is affected by outliers. However, at the end of the day, the choice of using normalization or standardization will depend on your problem and the machine learning algorithm you're going to use. There's no hard and fast rule to tell you where to normalize or standardize your data. So basically what you could do is you could have two models, one built over normalization and one build over standardization and see which is giving you better performance and take the one that gives you better results. That's what you can do. And at the end of the day, it's your choice. Okay. So now, which one should we use? Let's use standard scalar. That is basically the standardization. So let me write use standardization to scale the features. Okay. So basically, to do standardization, again, sklearn provides us a very simple way, and it's basically done using standard scalar. Normalization is done using min-max scalar, whereas standardization is done using standard scalar. So what do we do? Remember, where did we import train test split from? We imported it from sklearn.model selection. Now, where are we going to import our standard scalar from? Since it's a pre-processing technique, we are going to import it from pre-processing. Let's do a control space and we get the suggestion, and then we import standard. Again, let's do a control space to get standard scalar as the suggestion, and yes, we got it. So that's the first step. Now, what do we do after this? We have to call this standard scalar. We'll call it, instantiate it, and store it in a variable like this. So now basically SC is our standard scalar now. Now, what do we do? We have to actually convert each of the columns that we have to x minus mu by sigma, right? Where mu is the mean of the column and sigma is the standard deviation of the column. Now in standard scalar, we have two functions to do this. The first function that we have to invoke is called fit function, and the second one that we have to invoke is called the transform function. So what does the fit function do? Fit function merely figures out the mu and the sigma for the column. And transform function actually does the transformation for us, that is converts all the values into x minus mu by sigma. It converts all the x values into x minus mu by sigma. So fit transform just finds the mu and the sigma. Transform uses the mu and the sigma that are figured out by the fit method to actually make the transformation from x to x minus mu by sigma. Okay. Now we can combine these and create another function which does both the steps together, which is fit transform. Okay. Fit transform. So what does this fit transform do? It actually does both the steps together. That is, finds mu and sigma and then converts x to x minus mu by sigma. So it's a combination of fit and transform methods combined together. So let's perform the standard scalar on our x train. Okay. So fit transform has to be invoked first on SC, right? SC is our standard scalar. We have to invoke it on SC. So let's see fit transform. We see the suggestion. And then what we should provide at X train. We are performing the standard scalar only on our X train, right? And this is going to give us the scaled values. And then you can probably store it back in your X train. So now your X train is basically scaled using standardization. So for each of the columns, the mu is going to be 0 and the sigma is going to be 1. Now, let's do this for X test also. Now, one way to do it is like this. Do the same thing for X test. But this would mean that you are using different mu and sigma for your X test. Generally, what it's done is that you figure out the mu and the sigma for your training data and use the same mu and sigma for your testing data, the same mu and sigma. So that whenever new data also comes in, you don't have to find the mu and sigma then and there. You can use the same mu and sigma which you're using for your training data, testing data, and for the new data. So what we could do is either do it like this, or maybe what we can do is just use the transform function. Whatever mu and sigma were there for the training data, they will be used for your testing data also. So if you see your X test, it's going to be standardized. Now you see the values are some small values, right? So that's what we have done, that is performed our standardization. Now, since we are ready, now the next step would be to perform linear regression. So let me write perform linear regression uh, using sklearn dot. Basically, where does linear regression come from? It comes from linear model. Let's quickly revise. Where does our standard scalar come from? It comes from sklearn dot pre-processing. Where does our train test fit comes from? It comes from sklearn dot model selection. So where is our linear regression going to come from? I already mentioned here. So from sklearn dot linear model, let's see. If you do control space, you'll get a suggestion. Import linear regression like this. Now again, we have to invoke this linear regression and let's store it in a variable called reg. Okay. Now you have your training data ready with you. You have your testing data also ready with you. Now you want to build the model first. Obviously, you will build the model and then you will test it, right? So to build the model, which data is required? Let me show it to you. So this is X, this is Y. We divided it into two parts. One was training, the next was testing. So this is X train, this is Y train, this is X test, this is Y test, right? So you first need to build the model. To build the model, you should provide this data, that is the training data. So how do we build the model? We build the model using the fit method of linear regression. And to that, we have to provide the training data. We have to provide the X and the Y training both. So we provide our X train and we provide our Y train also. So we are saying that, hey, these are the X values, these are the Y values, see this data and come up with a linear regression model. And internally, it uses a variant of stochastic gradient descent to find out your coefficients and the intercept to basically find out your linear regression model. So let's do it. Let's run it. Since we have a very small data, it's not going to take much time. Okay. Now we have our linear regression with us, right? Now we can actually figure out what is our coefficient and the intercept. So basically, if you write intercept and then try to do control space, you'll get intercept. So this is going to be your W0 value. And then if you see your, if you try do a control space again, let's do it here, control space, and we get the suggestion. So these are the coefficients that you have. Okay, so basically, if you see if you had this data like gender, SSCP, SSCB, and so on, and then you had salary as the target, so how should your model look like? Salary is equals to W0 plus W1 gender plus W2 SSCP plus W3 SSCB and so on, right? So basically, what is the W0 value that we are getting? The W0 value in our linear regression is the intercept value. And then where are our W1, W2? They are basically here. This is W1, this is W2, this is W3, W4, and so on. Okay. So we have figured out our linear regression model now. We know the W's and we are good now. Now we have built a model and now it's time to test our model on the testing data. So once you have built the model using X train and Y train, now you give to your model only your X test and say, make the predictions for me. So it makes the predictions Y pred, say, and then you're going to compare them using the evaluation metrics that you have, which are MSE, RMSE, and R square. Okay. So now we are going to make the predictions. You build the model using the fit method. You are going to make the predictions using the predict method. Let's do a control space. 1 second. Let's do a control space and yes, the predict method. And we need to provide only the X test to it. Okay. So basically, what is this? It's 2.6052238 E plus 0.5. That means 2.6 into 10 to the power 5. E plus 0.5 means 10 to the power 5. And why are you getting some negative values when salary cannot be negative? The reason is your model does not know salary cannot be negative. Your computer or machine does not know that. So it can make negative predictions that are absolutely fine. So now let's store them in YPRED. Now the reason I was telling that don't do the standardization on your Y, because if you see here, the predictions that you get, they are real salaries. If you would have done standardization, then these would have been reduced to some small numbers. Now the predictions that you would be getting would be small numbers, then you will not be able to figure out what those small numbers represent and what are the exact salaries. So that's why we are not doing the standardization on our target. And generally standardization is done only for the independent attributes. Okay. So now this is our Y pred. Now we need to compare our Y test and Y predictions. Okay. We are going to use metrics for that. So from sklearn, I'm going to import metrics and now I'm going to call the metrics like MSE, RMSE, and so on. So metrics dot, let me say mean squared error. MSE is mean squared error, right? So if you see, you get this option, mean squared error. And then you just have to provide your Y test and Y predictions, and it's going to do the rest of the work for you. It's going to do 1 by n summation Y test minus Y predict whole square. That's going to do it, and you're going to get the final answer. Now, if you see, the MSc turns out to be very, very big here. What's the reason? The reason is that the salaries are big numbers. So even if there's a difference of, let's say, if your Y test is 60,000 and Y pred is 30,000, so 60,000 minus 30,000, which will be 30,000, and then you have to do the square of it, right? So that's why all the data points, when we do the y test minus y pred square for them, they are big values, and when we add them up, total becomes also big. So that's why the MSc is big here. How do we find out the RMSc? Just take the square root of this. And how can you do the square root? So np dot square root is the function, and just do the square root of this entire thing. So now this is your RMSc. You can also figure out your R score, or R squared, or coefficient of determination, which is written as R2 score. Let me just do a control space. Here we have R2 score, and you provide your Y test and Y predictions. So your coefficient of determination is turning out to be 76%. That means your model is decent, not very good, but okayish model. So that's all about linear regression. How can you improvise your linear regression model only? Maybe you can first select the features, select only important features. You can probably remove some of the features, that's do the feature subset selection. Then you can try to use your min-max scalar also and try to figure out. So there are some techniques that you can actually do to improve your linear regression only. Okay, so basically, you can improve your data so that your model gives you better results. And obviously, instead of using the linear regression, you could use any other regression model also to see if you're getting better results. So this is how you start off with one thing, then try to improvise on it. If you feel that 76% is less, you try to improvise on the data or improvise on the model and get better results. Okay, moving on to the next algorithm, which is logistic regression. Let's add the text column and say logistic regression. So the first thing, extract the independent and dependent variables. Independent and dependent variables. Now, if you see your DF, in logistic regression, we are basically solving a classification problem. That is, our target should be a category. So it should be status. That is, we want to predict whether the person will be placed or unplaced. That is, whether the status will be 1 or 0. So if you see, your X should contain what? It should contain all the columns except your status column, and your Y should contain your status column. So what I can do here is I can drop all the column, drop uh, only the status column, right? So if I drop status, and I have to put the axis as 1 also, because I'm trying to drop a column, and by default the axis is going to be 0. So if I do this, now what will happen is your status column will be dropped. Since I'm not setting in case is equals to true, it's not going to be done permanently. I will still have my DF having status, which is what is desired. I don't want to change my DF in any way. So if you see, you have your status here intact. So now I say the values of it. Basically, what I'm trying to do is I am just trying to convert it into an array, right? So this was your data frame. I just converted it into a array. And this is your X. Now, what will be your Y? You just have to take the status column. So you can take dot ilog colon comma minus 1, or you can do it in other way also. Just take the status column like this and take the values of it, which is basically now your X becomes a 2D array, Y becomes a 1D array, something similar which we had in our linear regression also. So half of it is going to be similar and just the other half is going to change. Okay. Now we have to split the data into training and testing. That's the same thing that we did above also in linear regression. So the first step is to get X and Y. First step is to find the independent and the target attributes, then do the train test split, then build the model, and then evaluate it on the testing data. So split the data into training and testing. So we know how do we do it. We have to just do the same thing again. So where do we get the train test split from? We get it from model selection. So from sklearn.model selection, I just write mo and do a control space so that it auto completes for me. Then import train test split. I get it here. Okay. Now, let me first run this. Now, to this train test split, what should I provide? Again, my X and my Y. The test size can be the same, zero point 0.3. You can change it also, it's up to you. You can set random state to anything. Let me set it as 30. And this is going to give me 4 arrays. The first is going to be X train, the second is going to be X test, the third is going to be Y train and Y test. The first two are 2D arrays and the next two are 1D arrays. We already know these things. Why are we doing these together? My main motive to do both of them together was so that if you understand one thing, you're able to understand the other also. Let me write it as linear and logistic regression. Okay, so we have X train, comma, X test, comma, Y train, comma, Y test. So now we have our data split into training and testing. Now, again, we can do the standardization here. Use standardization and then perform logistic regression. Again, the same thing has to be replicated again. So where do we get standard scalar from? From sklearn dot pre-processing. So I see pre-processing here, then I have to import standard scalar, and then I have to call it. And then first I'm going to do the standard scalar on my training data. So basically call this SC, and on that what method will be called? Fit and transform. Fit is going to figure out the mu and the sigma, and transform is actually going to do the transformation, which is converts X to X minus mu by sigma. So you call fit transform and then provide your X string. You use the same mu and sigma that you have for the training data only, and for the X test you do the transform. So this is the standardization that we perform in linear regression also. Okay. Now we have our, okay, let me write it as capital X train and capital X test. Now we have our standardized data. Now what we need to do is import logistic regression. So where did we import linear regression from? We imported it from linear model, right? So similarly, we are going to import logistic regression. Since it is closely derived from linear regression, the mathematics comes from linear regression, it is also a linear model. So similarly, logistic regression will also be taken from linear model. So from sklearn dot linear model, import logistic regression. Yes. Now the first step, you know, you need to invoke logistic regression. And maybe store it in, let's say, LR or log, because we've already studied logarithm, so I don't want to write log. Let me write it as classifier. Okay. Now, what I need to do is basically first thing, I need to build the model. How will I build the model? By providing the training and the testing data to my logistic regression. In linear regression also we had linear regression dot fit. Here also we'll have logistic regression dot fit. So the fit method is going to build the model for us, and we need to provide our X train and X test to it. And this is going to build the model for us. Okay. What's the problem? We have to provide our training data, right? So we have to provide our X train and Y train. We don't have to provide our testing data. So now the logistic regression is built for us. The next step would be to predict, to make the predictions on X test. And you're going to get the predictions as ones, zeros, and so on. Now, if you see the predictions that you have got are ones and zeros. So what is the threshold that it takes? It takes the threshold to be zero point 0.5. You can change the threshold also, but by default, it's taking the threshold as 0.5. You can, how do you change the threshold? I'll probably leave that to you to figure out, and then we can discuss it later. So now these are the predictions that you have. Now you need to compare your predictions with your y-test. So the next step would be to evaluate the model. Now, first let's draw the confusion matrix, right? So from sklearn, where does the confusion matrix come from? Since it's evaluation matrix, so it comes from matrix, and we have to import our confusion matrix. It does not give us any suggestions. Why so? Because matrix spelling is wrong. Matrix. Import, then do a control space, it gives us confusion matrix. And to the confusion matrix, we should provide two things, right? While calling y-test, y-pred. Now, if you see, you are going to get a 2D array. So basically, let me write it. 21, 0, 0, 41. So basically here are the actuals 0, 1. Here are the predicted 0, 1. So this is what? This is a true negative. This means it is predicted as 1, but it's actually wrong, which is it's a false positive. This means it's a false negative, and this means it's a true positive, right? So what I can do is basically the first value that I get is Tn, the second is Fp, the third one is Fn, and the fourth is Tp. So I can just actually get my Tn, Tp, Fp, and Fn from here. So how do I do that? If I take this confusion matrix and call the function ravel, which basically flattens the array, it's going to convert this 2D array into a 1D array. It flattens the array. And then the first value could be my true negatives, and I can just write them as Tn. Again, these are variables. You can use A, B, C, D also. For clarity, I'm using Tn, Tp, Fp, and Fn. So the first one is going to be Tn, the second one is going to be Fp, the third is Fn. So I'm going to write Tn, Fp, Fn, then the last one is Tp. So now I have my Tn, Fp, Fn, and Tp, right? Now, if I want to find out the precision, what is precision? Precision is basically TP by TP plus FP, right? Basically, out of all the predicted positives, how many of them were actually positives? So you just figure out your precision. So you can directly figure out your precision and recall in this way. Once you have your TN, FP, Fn, and TP. So you can figure out your precision, accuracy, recall, everything. What would be the accuracy? It would be Tn plus Tp divided by Tn plus Tp plus Fn plus Fp. We have to put the parentheses also because we want this thing to be evaluated first, this thing to be evaluated first, and then the division should happen. So this is our accuracy. And the accuracy is turning out to be 1 because if you see, we don't have any FP or FM. So this is kind of a good model where everything that we have is actually correct. Everything that we have predicted is correct. Does not happen normally since it's a very small data set. It's happening. Okay, we figured out this is our accuracy. We can also figure out the accuracy from something called as accuracy score, which is exactly the same. So it's going to use the exact same formula. So from sklearn dot metrics, we have to import accuracy score. Let's see control space if it gives us a suggestion. Yes, it gives us a suggestion. And then you say accuracy score, and then you give your y test and y pred. So you see, it's giving us the same accuracy score. It's calculating it in the exact same way. This we did manually. Here we are using sklearn. We can also figure out what is the ROC AUC score. So from sklearn.metrics, you have to import everything is inside metrics, right? All the evaluation metrics are inside metrics. So import ROC. Let's try to do control space. You get ROC AUC score. Okay. And then you just call this ROC AUC score, and to it give your y test and y predictions. So it's also coming out 1. Okay. Then what do we do is from sklearn dot metrics, we can also get all the precision recall, everything, everything in form of a report. And that's called the classification report, like this. And then what you can do is you can say classification report and just provide your y test and y predict. It turns out you see you have \n also here. So this is not in the right format. If you print it, then things would be proper. \n will not be written as \n, but it will actually be changing the line. So yes, now it looks fine. Okay. Since here most of the values are 1, so explaining it is a bit tricky. Like you won't be finding the difference between macro average and weighted average, but I'll try to explain you what's that. So what is this one? This is basically the precision that you get. That is TP by TP plus FP. Similarly, recall or the sensitivity. And similarly, F1 score will be precision into recall. Sorry, 2 into precision into recall divided by precision plus recall. Now, what is this? This is basically the the precision for class 0. So if your actual precision is the precision that you say, it's basically TP by TP plus FP, right? This is the precision. This is actually for your category 1. If you want to find it for category 0, then it is instead of the P, you are just going to write N, and vice versa, right? So here you will have Tn by Tn plus Fn. So instead of P, write N. Instead of N, write P. So this is the precision that you get for category 0. Generally, what precision and recall by default we say it is for category 1. But if you have to find for category 0, instead of the whatever formula is there, instead of N, just put a P, and instead of P, just put a N. So this is how you get the precision for category 0, recall for category 0, and F1 score again will be 2 into PR by P plus R. Now, what is this support? This support basically tells us that in the testing data, there are 21 points which have 0, actual value as 0, and there are 41 points which have actual value as 1. Okay, so Y test will be 0 for 21 points and Y test will be 1 for 41 points. Okay, now what is the macro average? Okay, accuracy you know. Accuracy, you know, and the total number of points are 62, right? Here, the total number of points are mentioned. Now, what is macro average? So, macro average for precision basically means that you take the average of these two, the arithmetic mean, that is 1 plus 1 by 2, which is 1. Again, since here 1 is there, that's why we are not able to see the difference. But it's basically the precisions that you have for 0 and 1 category, you divide it by, you add them up and divide by 2. That's take the arithmetic mean of those. Similarly for recall, similarly for F1 score. What happens in weighted average? In weighted average, you take the precision of category 0, multiply it with the probability of the point coming in category 0, which is 21 by 21 plus 41. That is the probability of the point coming in category 0 into the precision of category 1 plus the precision of category 1. So basically, this is precision of category 0 into the probability of category 0 plus precision of category 1 into the probability of category 1. Right? So again, here there's no difference. It turns out to be 1. But in other cases, it would be different. We used a very small data set and we were lucky that we got everything as 1. That is, there were no errors, no type 1, no type 2 errors. Okay, so this is what basically the weighted average would be. So weighted average would be calculated by taking the precision of a category into the probability of the point coming in that category, do it for all the points and sum it over. Whereas macro average is just the arithmetic mean of the two precisions that you have. So that's pretty much all about the classification report. You can get all the things from classification report only. So you don't have to calculate precision, recall, F1 score separately. And you get it for the other class also, that is class 0 as well. So that's the classification report, and you've got everything. This model is pretty good that we've made. We were lucky that we were able to get no errors. But generally, the data sets are not idealistic data sets. They are not small data sets. So generally, you won't get these results. Okay. So that's it for this session. We covered linear and logistic regression problem solving. And in the next class, we're going to start off with the new models. Thank you.